Hello, my name is Ankit Dakal, and I am a senior chemical engineering student here at Mississippi State University. Today, I'll be presenting on tunable full-color emissive heteroatom doped carbon quantum dots and their optical properties. Carbon dots, due to their unique optical properties, have been a potential candidate in many applications, such as bioimaging, optoelectronics, drug delivery, and sensing. Here we synthesized highly luminescent heteroatom doped carbon quantum dots by using BTNS2 and citric acid precursors. We use solvothermal method to synthesize these carbon dots. Figure 1 shows the reaction scheme for the synthesis of carbon quantum dots. 168 mg of BTNS2 was taken along with 50 mg of citric acid in a 2:1 molar ratio. This mixture was then dissolved in 15 ml of DMF and transferred to a Teflon-lined stainless steel autoclave. The autoclave was placed in oven for 12 hours at 210 degrees C. The synthesized carbon dots were then filtered through 0.2 micrometer PTFE membrane, and the filtrate was dialyzed for 3 days in a 3500 molecular weight cutoff cellulose sister membrane to remove any larger particles. The solution obtained was then dried using rotary evaporator to obtain the carbon dots. These carbon dots were characterized using UV visible spectrophotometer and FS5 spectrofluorimeter, which are shown in figure 2 and 3 respectively. When these carbon dots were dissolved in different solvents, we found out that they emitted different colors under the presence of UV light. We can see in figure 4 that the carbon dots emitted cyan color in DMF, red color in NaOH, green in water, and yellow color in HCl. The absorbance spectra for these carbon dots was obtained using the UV visible spectrophotometer. The spectra can be seen in figure 5a. Here we see around 2 peaks in the range of 200 to 450 nanometer, with the maximum being at around 200 to 250 nanometer. This peak corresponds to the pi to pi star transition in the conjugated system of carbon dots. In this transition, the electrons are transferred from the bonding pi orbital to an anti-bonding pi star orbital. Another peak at the range of 300 nanometer to 450 nanometer is seen. This peak is due to the N2 N2 pi star N2 pi star transition in the functional groups of the carbon dots. Also, emission spectra for the carbon dots in different solvents was obtained using the FS5 spectrofluorimeter. We can see different emission spectra for carbon dots in different solutions from figure B to E. We see that the maximum emission for carbon dots in different solvents is found out to be at different wavelengths, and we see that the maximum emission is redshifted with increasing the solvent polarity. The redshifted emission in the presence of acidic and basic medium is due to the protonation and deprotonation of the functional groups on the surface. Also, the emission maxima is redshifted while increasing the solvent polarity. This phenomenon is known as solvatochromism, where the color emission of a solute changes when dissolved in different solvents. The carbon dots produced by this method can be applicable in pH sensing due to this unique property. In the future, further analysis with different solvent polarity and pH will be required to clarify this trend and its application in pH sensing. This brings to the end of my presentation. I would like to thank Bagley College of Engineering for providing me this opportunity, and National Science Foundation for the grant. Thank you so much.